Lab 4, Circuits and Capacitors. The purpose of this lab was to understand the circuits with resistors in series and parallel, and to use multimeters to measure current and potential difference, and to examine RC circuits. The procedure for this lab was to use the circuit construction kit to create circuits in ideal condition, and we used that information to predict and analyze the results. Some fundamental physics principles that we used were the loop rule, which shows that the sum of potential difference in a round trip should equal to 0, and the node rule, which implies conservation of charge, meaning current going in equals current going out. Ohm's law shows resistance equals potential difference over current, and this is measured in ohm. In series circuit, we can see on the right that the predicted current was equal to the measured current of 0.02 amps, and when I reverse the ammeter, I am supposed to get a negative 0.02 amps. When this ammeter, one of the ammeter, was replaced with a voltmeter, you should be able to see the potential difference of 3 volts, and the ammeter remaining should read 0 amps, because the circuit is not closed. When the circuit was closed again, and we measured the potential difference across different points, and it measured to be 3 volts for 2 batteries, and negative 0.959 volts for 45 ohm resistor, and negative 2.041 volt for the 100 ohm resistor. And the current stayed constant at 0.02 amps. And as you can see on the bottom right, there's a graph of how the voltage changes across the circuit. There's an increase in voltage across the battery, and it decreases by the mentioned amount before at the different resistors. Looking at the ammeter in parallel circuit, you can see the new current was greater than the before current, which was 0.06 amps, and this is because now the current can move into ammeter without going through the 100 ohm resistor, and this makes them easier to move through the circuit. The resistance calculated from the measured values equal to be 47.95 ohms for the 47 ohm resistor and 102.05 ohm for the 100 ohm resistor, and it was measured to be 0 ohms for wire and ammeter. And this shows that we had the ideal model assumption of no resistance in wires and ammeter, which is different in real life example. By looking at the RC circuit on the right, when we were charging the capacitor with the battery, the light bulb started bright and it dimmed out. This showed the current was decreasing, and time that took for the bulb to dim out was 8.1 seconds and 20.2 seconds for a 20 ohm bulb. When the capacitor was discharging, there was no battery in the circuit, and the light bulb started bright and dimmed out again, meaning the current was decreasing, and the time it took for 10 ohm was 10.2 seconds and 20 ohm bulb was 19.7 seconds, which is approximately similar to what we measured when the capacitor was charging. Then by looking at the potential difference of the discharging capacitor, we looked at the linear relationship between ln of potential difference at t over initial potential difference, and when we plotted this for 20 seconds, you were able to see that the slope calculated was to be negative 0.164, while for our prediction, it was measured to be negative 0.167, and this was close enough that we can conclude they have a linear relationship. If I used an actual ammeter instead of the simulated ammeter, the actual ammeter will have small resistance, resulting in some potential difference across the ammeter. And if I used a real battery to charge a real capacitor with no resistor in the circuit, the capacitor will charge very quickly with no resistor. In the ideal model, as you can see on the bottom right, the prediction showed the capacitor reached full charge instantaneously with that flame going on. And in the real life model, we predict that it will be quickly charged as well, but it will take just a little bit longer because there are resistance in the wires. To conclude, current in the circuit is conserved according to the node rule, and the sum of potential difference around the circuit equals 0 according to loop rule. And we were able to see when the capacitor is charging and discharging, the light bulb starts bright and dims out because the current in the circuit decreases. And lastly, in real life model, there are small resistance in ammeter and wires, therefore we will have some potential difference across them.